project native. I am Tariq. This is Brendan, Abdul, Boris, Bill, and Matthew, and we are Team Native. For our Citizen project, we built a system that will allow our research robot to map the entire third floor of the new engineering building. The main motivation we chose this project was that we want to make our campus in general and indoor buildings more robot friendly. And what I mean by robot friendly is there's three main aspects we could think of. First of all is the robot has to have a physical access to the floor. Secondly, the robot has to know its surrounding, which is the situational awareness. And finally, the robot should have some control over the environment, which is basically performing the tasks that are assigned to do. For our project, what we're mainly focused on was the situational awareness aspect of this whole concept. For us, the native stands for navigating autonomously in a three-dimensional and interactive virtualization environment, which are the main goals for this project. So the first is the robot should be able to explore and map the floor independently, and the map should be within 0.02 meter of the actual floor plan that was given. The entire exploration will be done within 6 hours, and finally the map will be stored into an interactive cloud-based server for users to see the mapping process while it's happening, and also other third-party robots and users to download the map in the future.
This diagram here shows the three main components of our whole entire project. On this side, we have the Pioneer 3DX, which is used for the mapping, and it also communicates to our cloud server aspect up there, which takes in all the raw data and it stores it for both access by a user computer and also client access by a third-party robot. So what our map does is it provides that third-party robot knowledge of its surroundings, and then that way it will be able to use its own form of localization to move around in that map. And then for the Pioneer aspect, we brought our research robot here today, and the main component of it is the RGBD camera, which the RGB gives you the color of each voxel, and the depth gives you the distance of the voxel. And the voxel is a 3D pixel. Down here we have the LiDAR sensor, which is used for the 2D. And then also what we have is the sonar sensors, 360 around the robot, which gives obstacle avoidance for sag detection. And then the human detection features for obstacle avoidance is through the camera.
In order to map the floor, we are using SLAM, which stands for Simultaneous Localization and Mapping, implemented via RTAB map, developed by Dr. Laboa and Mashad. In the video below, you can see a feed recording of the robot mapping the floor. In the top left, you can see the robot's view from the camera, and below that, you can see the landmark database collection. And on the bottom left, you can see hypothesis testing where loop closure is detected. The RTAB map detects loop closure and allows the map to be corrected for any errors. And in order to minimize the error of loop closure, we are using Vertigo, which detects errors in images.
Once we create our 3D map and our 2D map, we need to store them. So for the 3D map, as you can see right here, is saved in a PLY file, format. The 2D map is saved in an occupancy grid format, so we save it as a PGM. However, we could have developed our own standard, but in order to ensure that future projects could use our design, we also saved it in terms of IEEE standard for robot map data navigation. These two maps that you see here were made when we manually mapped the floor using the Pioneer 3DX and the modified version of the ARC controller, which was originally developed by Lofaro Labs.
So now that we have a map, we need to be able to navigate through the map. And in order to do this, we have to implement a navigation module. We get the map and we have to process the map in order to be able to find a path in it. So what we do here, this is the unfiltered map, and then we create a dilation process. Through dilation, we actually bolden up the walls and the noise that may be in there. And then once we do eroding will actually remove the high frequencies, as you can see in this image right here. And the reason why we dilate first is because we don't want to lose some of the walls during the eroding process. So finally, we do another dilating, and that gives us a filter map. Once we're done processing the map, we're able to use a frontier finder module in order to find the next unexplored area. And once we have that, we actually feed that through the A-star algorithm. And what the A-star algorithm does is just converges to the lowest cost possible. And in this video here, you can see a simulation of the path planning. But even after we have done that path planning, we still have to account for obstacles that may be inside the path. So what we do is we've classified obstacles in two ways. We have static obstacles and we also have dynamic obstacles. And the static obstacles are essentially inanimate objects that may be in front of the P3DX. What we do, the way that we handle this is that we have the proximity sensors tell the obstacle handler that there may be an obstacle in front of it, and then we follow this procedure. We reverse, we stop, and then we replan. For dynamic obstacles, specifically humans, we have to implement computer vision algorithms. We have two computer vision algorithms. We have hard cascade phase, which recognizes faces, and then we have hog, which recognizes the body. And using these two computer vision algorithms, we're able to detect when a human may be in front of the P3DX. And we sort of handle it in a similar way. We stop, we wait for the human to either move out of the path, and if it's a false positive, or if the human decides that they don't want to get in the way, then we have to replan.
So once we complete our SLAM map, once we've navigated around the third floor, we also try to fit our 2D map onto the floor plans of the engineering building. So the way we do that is by estimating the affine transform. Given a location on the map, we can use that transform to transform it to the location with respect to the floor plans. This is a really useful transform, and this is really important because next time, should we decide to add a sensor to this robot and actually collect sensor data, we can say, okay, we want to go to this floor, this room. Let's look at the data from the sensor, and we can use an inverse of that transform to find that location on the map to navigate to.
All of our data is hosted on a remote server equipped with an Oracle SQL database and an independently designed, developed, and implemented web application. This web application is key because it's the central hub of all data communication. For example, the robot mapping computer. When the mapping computer is ready to upload its first map, it does so via Web API, or Application Programming Interface. The server will then respond with a unique ID. This ID allows the mapping computer to upload a new map. As you can see behind me, a user is accessing robot.gmu.edu, which you can access now if you'd like. The user will see the map in real time being updated as the mapping computer does so. One of the main goals of this project was to allow third-party computers and robots to download the map. Well, they can do this via a simple GET request on the API. When they do the GET request, the robot will download a map and all metadata required for localization.
So we've been able to map the engineering building in 3D and 2D. We've been able to autonomously navigate an autonomous navigation package. We've been able to develop a server to host all this information. And we've also, all this code that we've written down is open source, stored on GitHub, and additionally on Lofaro, wiki.lofarolabs.com, where we describe how we implement our system. This is Team Native. This shows our names, number of hours, and the contributions that we've done for this project. Our out-of-pocket cost wasn't as much since most of this was provided thanks to Lofaro Labs and Dassel and George Mason University. However, if we were contractors and we were contracted at $150 an hour, this project would have this much if we attribute the cost of our labor and the cost of these components. Additionally, throughout this year's senior design, we've also done a number of outreach programs. We've gone to the Smithsonian Robots Expo. We've also gone to the National Maker Faire. We've gone to Nova Mini Maker Faire Convention. And we've also gone to the Virginia Tech Maker Festival. The purpose of this project isn't just to make this robot to build a map. The purpose is that we want to make these buildings more robot friendly. We want to be able to develop a map, put some landmarks on it, and we want to essentially make this entire campus a robot friendly campus. Thank you.
Questions, please?
What sort of simulations did you do prior before mapping the actual robot? Did that help you at all, like plan ahead and then try to implement it? And then, I guess, what sort of challenges did you overcome?
We used a gazebo simulator to simulate this very robot and the Kinect sensor and the Habib laser. Some issues that we faced was that, such as the sonar sensors, and sonar sensors weren't as implemented in the simulation. Additionally, the quality led to a number of issues due to some hardware issues, and some communication between the robot and our programmer. So yes, to answer your question, yeah, yes, it did help us a great deal.
So you can hear it coming.
Yeah, more questions? One more, I guess. No? Harder one. All right, thank you very much.